Now this is the kind of new stuff that we're looking at here. It says using 4 inscribed rectangles of equal width, and they say lower sum. Then you see, like if you look at number 2, just so you can kind of see some of the difference, this is upper sum, okay? And then this one says midpoint sum on it. So there's a couple different ways to set it up. What we're doing is we're setting up rectangles. When it says inscribed rectangles, these mean rectangles that are basically under the curve. And you're either going to start them on the lower side or the upper side or the middle. So if it says lower sum, what we're essentially doing, and it says 0 to 4, so just be careful with that because we don't want to go the whole way to 5. We're setting ourselves up rectangles where the left corner, when it says lower sum, we're going left corner. Okay, and I don't want to write that big because we need our room there. But you're going to set yourself up rectangles that on the left corner, they touch the curve. So starting at 0, I'm going to start by drawing myself a rectangle here that has its corner, its left corner on the curve. So see how that touches right at 0 on the curve? So my next one, my second rectangle, would start with its left corner right there. So then my second rectangle would look like this. My third rectangle would also start with its left corner on the curve, and I would draw it here. I was
saying there's like ACT, SAT problems.
Similar. And then our last one, because we're only going to 4, will have its left corner on the curve right there. Any issue with how we're drawing our rectangles here? Now, how do you find area of a rectangle? Okay, length times width. And now this is not going to be an estimation because you actually have an equation to find the height of these, yes? The first one's easy, okay? So we're going to say our area is equal to, and really, how do you find total area? We're just going to add them all up, right? So we're going to say our area is approximately, and we're going to go through each of our rectangles. So my first area is going to be what? 1, because it's just 1 times 1, right? My second area, also easy. What is that area? 2 times 1. Now the third one is where we hit one that's not at an exactly nice number, right? Okay, we do not estimate because we have this, okay? So when I'm trying to find the height of this one right there, what number am I plugging into my equation? 2, right? Because that's where that corner is. Do we all see that? This lines up right here at 2, okay? So when I plug in 2 right there, what am I going to get from that equation? Root 2 plus 1. And all of these rectangles have a side length of 1 at the bottom, so that's just times 1, right? So then to do our last one, this one, we have what? We plug in 3. So our last area would be what? Root 3 plus 1. Now, if this was a calculator problem, you'd type this all in and get yourself a estimate area. We call this an estimate because obviously, can you see if we draw those rectangles, that's not going to be an exact area. We're missing some area on that one, right? All right, so let's do the same thing, but we're going to go ahead and look at our second one. This is called upper sum. Can you guess how this is different?
Do we simplify?
We don't need to simplify. Nope. Just show writing out your area the whole way through. Done. So upper sum, how do you think we're going to construct our rectangles differently?
Upside down.
It's going to be the right corner touches the curve. So for this first one, if I'm going to do a first rectangle, but I want my right corner to touch it, this time this one's going to go here. Right, so this one's going to go over, which means when we get our final estimate for this, what do you think it's going to be? Larger than the area, right? So then my second rectangle is going to go here. Right corner touches. Third one, right corner touches. And fourth one, right corner touches. Okay? Now, if you're given a picture, it's very easy for us to draw like the rectangles and do this way. What I will tell you is as we get into the rest of this and there's no picture given to you, draw it anyway. Like you're not going to get it right if you don't draw it. Because even me, if I look at like a table of values, I'm not picking what's the right one when I do like the right and the left corners. Like I need to see this to do it. So draw yourself a picture. It's not going to waste your time. Okay. So when I do my area for this one, we're going to add it all up again. Okay. The first one. Okay. To find what this is, well, we know what this is right here, right? So what's my first area? 2. My second one, I need to know what this is. And so what x value is that going to correspond to? 2. So when I plug that in, my second area is going to be root 2 plus 1. What about my third rectangle? Root 3 plus 1. And, okay, so really just 3, yeah? So that we would say is an overestimate, right? Because, and therefore, because we know the first two, the first one was an underestimate, right? Second one was an overestimate. So what would you say on this one? We would say that our area, our true area, falls between these two. Right? And I'm just using what we wrote for our answers here. Ran out of room there. But first area is lower, second area is higher. So the more accurate we can estimate this, the better, right? So that's what leads you kind of to the third one, midpoint sum, which you can guess what? We set the height of our rectangles based off of the midpoint of those two. Instead of setting it on the left or setting it on the right, we now go through the midpoint. So when we set up our rectangles on this one, I'm going to say, okay, here is my midpoint on this. Okay, my rectangle is going to go directly through the x midpoint. It's the x midpoint. It's not the y. Okay? So then my second one is going to go through the midpoint on this one. We'll say right here. Okay? And our third one will go through the midpoint on the third one. And same with the fourth one. Now, what makes this better just visually? Can you kind of see it? So like on the first rectangle, yeah, I've got a little bit extra there, and I've got a little bit left out here. But it keeps getting less and less because that curve flattens out. So what we're kind of hoping on this estimate is that it's a little bit more accurate because we have a little more but a little bit less, and we're kind of hoping it evens out, right? So now when we construct our area formula from this one, we're basing it off the halfway point on each one, right? So like for that first area, what x value are we using? 0.5. So again, a lot of this is going to be estimates, so we don't need to like say 1/2 and do fancy things with the square root. We're just going to say square root of 0.5 plus 1. So then the second one would be square root of 1.5 plus 1. Third one, square root of 2.5 plus 1. And last, square root of 3.5 plus 1. So, and we kind of already talked about this, these questions below. I'm just kind of going through it as we talk. But would you say that the midpoint one is more accurate than the other ones? Yeah, because we have a little give, a little take. And
what would you say, like proportional maybe?
yeah, it'd be a bit, the over and under is a little bit proportional to each other, so we're hoping it's more accurate. Okay, so we would say that this is the most accurate. So what do you think? We've gone through 3 different options: left hand, right hand, or lower and upper, and midpoint. What do you think could make it more accurate?
We used a calculator.
If you used a calculator, yes.
Them and like divide by 2.
So, yep. What about different shapes?
The ones that have like symmetry and stuff.
Mm-hmm. So you could, yeah, one thing you could do is you could go smaller on the rectangles. You could use more rectangles because that would be more accurate as you go. You could use different shapes. What kind of shapes do you think would fit under that curve better? Trapezoids. That's one of them.
Oh, yeah.
Okay.
Ingrid said trapezoid.
Yep. So trapezoids would be more accurate because they would fit under the curve a little bit better. So you could do more of them. At some point, though, you see that it's never going to kind of be an exact science on this. These are always going to be estimates, okay? Which will lead to what we're doing in the second one, okay? So before we leave this, we're just going to talk about a couple of these and how you would set them up. A little bit less of like the area formulas and a little bit more of just talking setup. So one thing we said was that you could use trapezoids instead. So if I use trapezoids on this, what that would do is it would say this side, connect here with a diagonal. Use this trapezoid. And so that gets a lot closer to the curve, especially if it's a flatter curve. So you see on the second one,
Doesn't it leave stuff out?
it does. And so the trapezoid for this one, now this depends on the concavity. This is a concave down curve. Because this curve is concave down, this will be an underestimate. What would happen if it was concave up?
Overestimate.
It would be an overestimate, okay?
Oh, wait, this is really accurate for these next.
Yeah, this is actually pretty accurate for this one. It would be a little bit under,
The first one that's not.
okay? Now, here's the larger question. Do you remember how to find area of a trapezoid?
The top base plus the bottom base times the height divided by 2.
1/2 base 1 plus base 2 times the height. Okay? Now, for all of these, what's the height for every single one of these? 1, because the height, we're thinking kind of like sideways.
Oh,
Yeah? Because for a trapezoid, this is your base, and this is your height, right? You got to think about that trapezoid sideways. Yeah? So this will be the last formula we write out, and then we'll just look at drawing some of them to see what the setup would look like. So my area for this one, total area, we're just going to list it all out. That first trapezoid would be, now, are they all going to have a 1/2 in front of them?
Yeah.
Yeah, so are we okay if we just do 1/2 outside of a bracket and just not worry about it for every single one?
So smart.
It is, yeah, isn't it? So the first trapezoid, base 1 plus base 2 would be what?
3.
3. Do I have to multiply by the height of 1? No. Okay. So that's my first one. Second one, base 1 is 2. How would we represent base 2, which is this guy here? Okay, well, we had that formula, remember?
Oh, is this for
This is the same curve, same curve. So that was the square root of x plus 1. Okay, so what x are we using for that base?
Oh, we can use the same.
2.5.
Hmm?
Oh my God, 2.
2. So that would be root 2 plus 1, yeah?
How do we know whether to use the 1 or the 2?
We already used the 1 with this one. That was this 2.
Got it.
So I'm just doing the first one plus the second one, yeah? All right, so then let's look at the third one. If I'm doing these two, I'm going these two.
You would have to do it for both of them.
So I would do root 2 plus 1 for the first one, and what? Root 3 plus 1 for the second one.
Because you're using the x values.
Yes. And then the last one, since I'm color coding, we'll go this one and this one, yeah? What are those two going to be represented by? Root 3 plus 1
And 3.
and just 3, yeah? Now, do we need to simplify this? Nope. The main idea is just being able to represent the area, okay? All right, so now let's just talk about if they gave you different ways to set it up. We're just drawing the next couple. Because at this point, we're starting to get the idea of the rectangles and all that good stuff, yeah? These just work out the same way every time. Okay, so now you're going to see some different language here. Right-hand Riemann sum. Okay, this is the fancy name for it. Riemann. This is like the upper one that we did on the first page. So when it says right hand, that means we want our rectangles to connect on the right side.
Okay.
When it says left-hand Riemann sum, we want our rectangles to connect on the left side, okay? And you have to be able to set this up based off the boundaries they give you, and like it says 8 rectangles or whatever, okay? So we want to find the area on 0 to 4 using 8 rectangles whose height is determined by the right side, okay? So if we want to go 0 to 4, we need to, and we're just drawing on this, right? So if we go 0 to 4, if I split it into 4 sub-intervals, and then split those in half, that would give me my rectangles, right? But we have to be able to draw each of our rectangles, the tops of them, so that the right corner is connected. So when I split these up, I'm going to go ahead and say, Okay, here's my splits, but I haven't like drawn the tops of them yet, right? So for each one of those, we start in the right corner and draw across. So this one would go from here over. This one would go from here over, and so on. Do you see why drawing it is so important to tell which values you're using on each one? If we were to do our equations? Yeah. So just generically, like I said, I'm not going to go through every single formula on this one, but to do your area on this one, okay, it would be a very long formula, but just generically with this. Each one of these rectangles has what side to side width? 1/2, because that's how we set them up, right? So each of these would be 1/2 times, you could really just do all the heights added together, right?
Right.
So for each of these heights, you would be using the actual formula. This is not a nice one, and that's why we're not going to actually plug it in. This would be a total calculator question, right? So you would say, all right, I'm going to do y of, for the first rectangle, what x value would you plug in? 0.5. The second one, you would plug in y of 1. The third one, y of 1.5, dot, 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 all the way out to the last one would be y of 4. Yes? And I'm never going to get like which x values I have to plug into that without drawing. Like, I'll just be very honest. I'm not doing that without drawing.
So would it tell us what type of shape we're drawing?
Yes. Yeah, they'll specifically say use a right-hand Riemann sum, and therefore you could do the right side and do all that.
But it would say like use a rectangle versus a triangle, or would you assume-
So Riemann sums are assumed to be rectangles. Okay, Riemann sums are always rectangles, so they will say specifically trapezoidal sum if you're to do those. Okay?
Is this the one where you put the y and like the y1 in the graphic
Mm-hmm.
part?
Yep, we'd use that same calculator notation. Yep, you do your y1 and do all that.
But the only word you have to show is just.
Okay?
And it will tell you how many rectangles at once?
It usually does, yes, because they can't really tell you what to do. Like, they can't expect you to get a certain estimate without telling you how to split it up.
Right. I was wondering
Yeah.
why we did 8 and then I saw the
Yeah.
problem.
All right, so what I want you to do, rather than me doing this, is do the same exact thing we just did, but using on 9, the left hand, and on 10, the midpoint. But don't do formulas, just sketch. Okay, just practice sketching in what the rectangles would look like. Once I kind of divide it up into 8 parts, I go to each rectangle and I say, okay, here's my midpoint. Okay? So if I use that midpoint, it's going to go across here. And then I do the second one. I say, here's the midpoint. This one's going to go across right there. Third one, here's the midpoint. Draw a flat line right there. Does that help? Yeah? No?
It's just something from the far right. Like the,
On like what we do over here?
yeah.
So for that one, if I draw in so there's my midpoint. Are we all okay with the midpoint? You draw in a horizontal line right there.
And just connect.
And then connect.
Oh, I see. Okay.
Yeah?
So we don't need that excess line that's on the far right,
You do.
like over the pink?
Oh, yeah, you probably don't need that to be up there.
Okay.
Yeah, like that part.
Yeah.
We're not going to use that. But sometimes it does show you how that part's like under the curve. But so then like this one, I draw my midpoint line, I draw a horizontal line, and then I connect it. Midpoint, horizontal line, connect. This one's almost exactly flat right there. This one, midpoint, horizontal line, except it connects on the right.
These notes actually are not taken,
No.
because we already got there too.
All right. How do we feel about that? Okay? So integrals, just like derivatives always represent slope, the integral represents area. So when you are integrating, you are finding the area under a curve. Okay, so integrals can give us positive or negative values depending on whether the curve lies above or below the x-axis. Okay. So when you do integrals, we're going to do them a couple different ways. We already know how to integrate, and so if you have an equation that you can integrate, you can do that and use the endpoints to plug in. We're going to see that in a minute. Or if you have something like that's just a graph, you can represent the integral itself without the equation by just finding the area under the curve. And this is like geometric stuff, okay? So like, for example, what is this graph that we have right here? It's absolute value. Do we know how to integrate absolute value? Have we talked about that? Nope. And you're never going to be able to algebraically integrate absolute value. However, you can find the area specifically under the curve. So let's say I wanted to find the area between x equals -2 and +2. So how would we do this without actually being able to integrate? We would just draw ourselves, okay, here is -2, here is +2. What you are finding, if I said, okay, I want to do now the integral of the absolute value of x, but we want it specifically to be between -2 and 2. These are called boundaries. And they just tell you to find the area between those two.
Is that actually
Yep, little 2 up there. Yep, from this one to this one. So what you're doing is just finding the area under the curve in these sections. Those are triangles. How do you find area in those triangles?
Base times height.
Yes. So this one in particular would be 1/2 times 2 times 2, okay? Which just gives me what? 2. What about this one? Is it any different? No. So what's my total area under the curve between those two? 4. And so sometimes they will ask you to integrate something that you don't know how to integrate algebraically, but it's just asking you to find area. Okay? So same type of thing with the second one. Let's say I wanted to find the area between -2 and 2 on this one. What is that one?
It's a half circle.
It's a half circle. What's the equation for that? Square root of, what's the radius? R squared, what's that? 4 minus x squared. Oops, I forgot my dx, guys.
Square root of r squared.
Minus x squared. Now again, do I really want to go through u substitution on that and find the area under the curve? No, I don't want to do that. It's easier for me to say, can I just find area of this half circle? Yes. How do you find area of that? Okay, I would do pi times my radius squared over 2. What are we going to get for that area? 2 pi. So these two were given graphs. Sometimes they will not give you a graph and they'll just ask you to go ahead and draw it yourself. Okay? This one, could we integrate in A ourselves and find that? Without doing like an area thing? Yes. This one just says sketch the region though. So let's see what this would look like. What kind of graph is this? A line. So 1, 2, 3, 4, 5. My line starts at 5 and has a slope of -2. Yes? Or +2, excuse me, but I went down 2. Okay, so there's my line. What area do I want to find on that one? The area between what and what? 0 and 2. Okay, so at 2, what's my y value up here? 9. We know because we count using the slope, yeah? So if I want to find the area under the curve from 0 to 2, that's essentially saying, if I just kind of drop a line down there, find this area, right? Integrate from 0 to 2 means find that area under the curve. What shape is that? A trapezoid. So I would say my area is 1/2. What's my base 1? 2 is the height on that one, right? No, you're fine. So 5 plus 9 is my base 2. times my height of 2. So what do I get for my area for that? 14. Now this, we didn't actually have to solve that, but we just did for fun, okay? You could also represent B. Okay, what does the sign graph look like? Oh, look how all the parent functions are coming back. Okay, where does sign start? 0. Forwards, backwards, back to 2 pi. Yeah? So if I want to find the area under the curve, what am I shading for that? Okay, I'm shading this here. It's always to the x-axis. And what else? This part here. Okay? Now, we haven't seen it yet, but we did fill in the blanks where it says area can be, or integrals can give you positive or negative values based off of whether your graph is above or below the x-axis. Okay? Yes. So like without knowing any numbers on this one, this area is 0. How do I know that?
Same thing, but mine's positive.
Because this is a positive number, this is a negative number, and they're the same. So that total area would be 0. Now the easiest thing to get wrong right now on this is going to be forgetting to make that area negative when we do those pieces. It'll be just, we'll have to think about it, okay?
If this went like one more, would it just be pi?
So that area is not specifically pi, because it would be like a sign value.
Yeah.
All right, so let's go back and finish here, because I got to roll. We got a minute. Here we go, we're doing well. So, a couple things. If you integrate from A to A, these are the same x values. Your area is automatically going to be 0. Okay, because there's no area if your x value has not changed. If you integrate from A to B of a function, it is the opposite if you flip the boundaries, B to A, negative that value. You can also split up integrals, okay? So instead of saying from A to B, let's say this was from 0 to 10. Let's say you can't find the whole area from 0 to 10. You could find the area from 0 to 4 and add it to the area from 4 to 10. So you can split these into 2 pieces and put them together. And as we stated before, because the bell's about to ring here, you can always take a constant out front. Okay? The rest of this is just using those, and it's not that difficult. I will do here, like this afternoon, I'll do like a 5-minute video on that, like 5, and I'll post it for you guys, okay? Okay, so for our last example here, we are given that the integral of f of x from 0 to 5 is 10, and we're also told that the integral from 5 to 7 is 3. So we're going to use that information and the properties that we just talked about up here in order to help us figure that out. So if we want to find the entire integral from 0 to 7, we don't have that exact information given, but we do know from our property C up here that you can find a full integral by adding together the pieces. So you could say the integral from 0 to 5 plus the integral from 5 to 7 would give me the full integral from 0 to 7. So in this case, this integral, the first one is 10, the second integral is 3, therefore the total integral would be 13. So for B, we will use the flip. If we know 0 to 5 is 10, we know from our second property that if you flip it, it just becomes negative. So the integral from 0 to 5 flips on this one and becomes the opposite of the integral from 0 to 5, which means it would be negative 10. C is the easiest one. When we integrate from 5 to 5, that's our first property that we used up here. If we integrate from the same letter or the same number to itself, it always is going to give us 0. And last but not least, if we have D, this is the one with the constant k out front. This is the same as you're allowed to pull that constant out and say multiply that by the integral from 0 to 5 of f of x dx. Therefore, that is 3 times the integral from 0 to 5 is 10, therefore 30.